Hello everyone, a warm welcome to L&T College Multimedia Studio Muzaffarpur. This is Dr. Sunil Kumar from L&T College Muzaffarpur. Today I have brought a more interesting and exciting topics, that is what we recall it as electrochemical cell. And electrochemical cell is nothing but it is a device that converts chemical energy into electrical energy, and based on the redox process or redox reactions, right? So this electrochemical setup actually has been shown in this particular fashions, where we have a two containers, right? This is container 1 and this is container 2, right? These two containers are actually filled with electrolyte, right? Electrolyte means this is actually aqueous solution. So first container, this is your first container which contains aqueous solution of zinc sulfate, and second container which contains aqueous solution of copper sulfate. Here we are going to focus on actually zinc copper galvanic cell. So that is a special type of electrochemical cell. So electrochemical cell is actually based on the redox reactions or redox process, and electrochemical cell actually composed of electrodes and solutions, and the solution actually is electrolyte, right? So zinc and copper galvanic cell, so this is the setup where I have shown. And in these two containers, in the first container we have dipped, so this is your zinc plate, and in the second container we have dipped copper plate, right? So copper plate is dipped in copper sulfate solutions, and zinc plate is dipped in zinc sulfate aqueous solutions. So here all electrolytes are obtained through dissolution of a particular salt, that is zinc sulfate and copper sulfate, in aqueous medium, right? Now one another thing has been inserted between these two containers, so that is actually inverted U shaped. This is your inverted U shape. This is called salt bridge, right? And that salt bridge contains strong electrolytes. So that is like you can see this salt bridge actually KCl or KNO3, that is actually strong electrolyte, and that electrolyte is actually in agar gel. uh, this electrolyte solution actually contains agar gel in this system, and this salt bridge actually this is a porous system, right? So the salt bridge lower part is porous, or you can simply say whole part may be porous, and it actually helps to transport selective ions in these two containers, right? So the main function and behavior of this particular salt bridge is to connect these two containers and these two metallic plates. So first metallic plate, that is zinc, and second metallic plate, that is copper, right? So both these plates actually are dipped in its aqueous solution of salts, that is electrolyte, right? And these two metals actually they are connected uh, by voltameter, right? So this is the external source, that is voltameter, right? So the chemical energy is stored in these solutions, right? So this is called first half cell, and this is called second half cells, right? So redox reactions are composed with oxidation half cells and reduction half cells, right? So these two plates have actually different works. So that is actually, this is your uh, anode, right? So this is called actually anode, right? And this is called cathode, right? So anode has its different function, whereas cathode has its different function. So anode is actually responsible for oxidation, and cathode is responsible for reduction reactions. So what happens actually here is that when zinc metal is dipped into this container containing aqueous zinc sulfate solution, and when copper plate is dipped in the second container having aqueous copper sulfate solutions, and both these containers are connected with a inverted shaped salt bridge, so which contains strong electrolytes, right, saturated by agar gel. Now these two plates are connected by a voltmeter, right, which will actually reflect the information of electrical energy, how much electrical energy is produced in this particular setup. So that will be actually measured by voltmeter, right? So this is the actually component of electrochemical cell. Electrochemical cell means, so that is, it is the part of electrochemistry, and electrochemistry actually based on the oxidation and reduction reactions to produce a overall redox reactions. So any redox reactions that contains two half cell reactions, that is oxidation reactions, and another one is a reduction reactions. So here, that is your three component, that is electrolyte, and that is metal electrodes, right? So first metal electrode, that is zinc, and second metal electrode, that is copper, and third component is salt bridge, right? Now when the setup is complete, right, what happens actually is that this is your zinc plate, right, and this is your copper plate. What happens? There is an interface between zinc and zinc sulfate aqueous electrolyte. So this is actually shown by this vertical line. So this vertical line actually, it is an interface between solid zinc plate and aqueous zinc sulfate, right? So this is the actually one pair for half cell reaction, and here we have shown two vertical line, right? So this two vertical line actually is called salt bridge. This is your salt bridge, and another component, that is copper solid, is actually attached with this particle line, and this vertical line is a interface, and this copper solid is dipped into its solution, that is copper sulfate aqueous solution. So this is the cell diagram. So this is what we call cell diagram. So any particular electrochemical cell that is actually composed of three components, that is first component, and which is actually called anodic component, and another component that is called cathodic component, and both anodic component and cathodic component, so they are connected by salt bridge, and the salt bridge has capacity to produce selective ions, and they will mobilize the solutions to perform its activity to complete this particular electrochemical cell, right? So what happens once this zinc plate is inserted in this particular container having ZnSO4 aqueous solution, so there is a potential, right? So actually solid and liquid junction, that is called special potentials. Here one cathode, that is copper solid, is dipped in copper sulfate solutions. So here solid and liquid interface, here solid and liquid interface. Now what happens if this is connected by voltammeters? Then there is a actually spontaneously potential difference is created in this particular setup, and potential difference is due to the, this is for cathode component and this is for anode component. So the potential difference between two components actually will be result into the conversion of electrical a chemical energy into electrical energy, right? Now here zinc plate actually undergo into the solution as a form of Zn2 plus aqueous, right? Leaving behind electrons on its surface, right? So that is why it is negatively charged, or it has a negative polar, right? In this particular component, what happens? From the solution, Cu2 plus aqueous will undergo on this copper plate, and this is actually become positively charged, right? So this is positively charged, means cathode has positive sign and anode has negative sign. Since copper 2 plus actually flows on its surface, so that is actually positively charged. So here a positively charged cathode and negatively charged anode. So there is a difference of potential that causes the reactions to proceed to produce the product, right? So here what happens actually in this particular setup is, that is actually your, in the first component, that is zinc solid undergo Zn2 plus aqueous, right? That will release 2 electron. So this is called oxidation, because here the oxidation state of zinc is 0 and here oxidation state of zinc is 2 plus. So this is your oxidation. This is your oxidation. This is your oxidation reaction. And the potential which is generated between zinc 2 plus and its solution, that is zinc sulfate aqueous solution, it is actually E0 anode 0.76 volt. So that is, we have shown here Zn2 plus 2 Zn minus 0.76. Right? And another half cell reaction is actually copper 2 plus from the copper sulfate solution will receive 2 electrons, which is coming from the external circuits from anode to cathode. Then this will be reduced Cu as a solid, and this is actually reduction reaction where copper has oxidation number 2 and this copper solid has oxidation number 0. So here decrease of oxidation number indicates, so that is reduction reaction, right? Reduction reactions. Now look at these two equations. This is first equation and this is second equation, and the potential for this particular half cell reaction, that is Cu2 plus oblique Cu is equal to the value which I have shown here, 0.34 volt. 34 volt. So this is the positive quantity actually, and this is the negative quantity. When Zn2 plus will undergo into zinc, then it has minus 0.76 volt. So any particular redox reactions actually composed of two half cell reactions, that is oxidation half cell reactions and reduction half cell reactions. So for oxidation half cell reactions, the E0 anode is 0.76 volt, and for reduction half cells reactions, E0 anode, you can say E0 anode, not anode, this is your cathode. So this is your cathode, 0.34 volt. Then overall reaction look like that: zinc solid plus copper 2 plus aqueous, right? Zn2 plus aqueous plus copper solid, right? So look at this particular redox reactions. So overall, this is your redox reactions occurring in a electrochemical cell, and electrochemical cell is nothing but zinc copper galvanic cell, right? So what happens? Zinc solid is dissolved and undergo into the solution, right? So this undergo into the solution, and copper 2 plus aqueous from the electrolyte, it actually converted into copper solid. So copper solid material is deposited on cathode, right? Whereas zinc solid material undergo dissolution and undergo into the electrolyte solutions, that is zinc sulfate solution. So zinc solid will be increase the concentration of zinc sulfate solutions, whereas copper 2 plus solution increase the production of the copper at the cathode. So here in one case the concentration of the zinc sulfate solution increases, and another case the concentration of copper sulfate solution decreases, right? So in this case, since zinc 2 plus is removing from this surface and it will go into this solution, so the concentration of zinc sulfate solution increases here, right? Here copper sulfate solutions decreases. So this differences of solutions actually creates a potential difference, and that potential difference actually responsible for the movement of charge, that is electron, from external circuit. So this is the external circuit, and from anode to cathode, right? Electrons are traveled from anode to cathode always, right? For a zinc copper galvanic cell, the electrons are transferred from this anode to cathode. It means Zn2 plus is due to the oxidation of these surface, this zinc plate, and here the copper 2 plus is converted into copper solid. It means here copper is deposited on the surface of this copper plate, right? Copper plate. So what happens here? Zinc reducing the weight or mass of this plate because it will go into the solutions, whereas here copper 2 plus itself deposited as copper onto this particular copper surface or copper plate. So mass of the cathode increases and mass of the anode decreases. So here mass increases and here mass decreases, right? So this is also you can say this is the difference between these two type of metal plates. So here mass decreases, here mass increases. So after the passage of time, what happens? All the overall reactions, that is all the zinc solid with the help of copper 2 plus in the container 2 will actually produce zinc 2 plus aqueous and copper solid. So after a time, actually all the reactant side, all the reactants, they are consumed through a particular redox process and as a converted into the products. So the products of this overall particular redox reaction, that is zinc 2 plus and copper solid. So electrochemical cell that produce a particular type of products in a redox reactions, right? So what happens now? If there is increase of concentration of Zn2 plus aqueous, right? So how this will be neutralized? Increased concentration of zinc 2 plus will be neutralized through the movement of selective ions. So here it is positive 2 charge. So the negative charge or negative ions will be coming from this salt bridge, right? And that will neutralize the solutions. And from this side, the positive ions, because positive ions is decreasing in this particular solution, so the neutrality is maintained through the movement of positive ion in this fashion. So this is the beauty of salt bridge. Actually, it is a porous, and that actually does not interfere the redox reactions or any particular interaction with zinc or cation or anion of a particular container. So these ions does not react with the zinc 2 plus or sulfate 2 minus. Here, any of the ions, that is in case of potassium ion, that does not react with copper 2 plus or sulfate 2 minus aqueous solution. So only the role of this salt bridge is to maintain the conduction and conduction between these two solutions through maintaining the electron neutrality of the solutions, right? So now what happens? There is a potential difference that cause the movement of electrons from anode to cathode, right? Here anode is responsible for oxidation and cathode is responsible for reduction reactions. So this oxidation and reduction reactions particularly is measured in with a voltmeter, and that voltmeter will gives us idea about the what is the potential of this particular electrochemical cell, and depending on the deflections of this voltmeter symbol will actually provides us idea about the cell potential and of this particular setup, right? So every two combinations, actually different type of cell potential is obtained, and that will be actually characteristic to the anodic component and cathodic component. Now here what happens, the cell potential, that is actually E0, Zn2 plus and zinc. Here zinc 2 plus is reduced as a zinc, so it is actually standard reduction potential. E naught stands for standard reduction potential, here minus 0.76 volt. Here standard reduction potential, that is copper 2 plus to copper, that is 0.34 volt. So that is positive sign, here it is negative signs. So because it is negatively charged here and here it is a positively charged, so here that is your higher potentials, because here weight or mass of the cathode increases. Here potential is low because mass is actually mass of the plate is decreased after time, so it is a lower potential. So what is potential difference? So the potential difference is actually E0 cell, E0 anode, not anode. So that is actually, this is your cathode minus E0 anode, right? So this is your 0.76 volt for this particular oxidation, and here this is your 0.34 volt for reduction. So here what you can say, 0.34 minus, so this is your standard reduction potential for the anode. So here the value is 0.76 and this is your minus 0.76. So here this is equal to 1.10 volt. right? So this is your zinc 2 plus and zinc. This is your minus 0.76 volt. Now what happens here? Oxidation potential is equal to minus of reduction potential. It means oxidation and reduction potentials are actually same value, but they have opposite sign. So if the oxidation potential is positive, then its negative potential will be negative, and vice versa. So overall, each cell at standard state means actually at 25 degree centigrade, it means at 298 Kelvin and 1 atmosphere pressure and 1 molar concentration based electrochemical cell actually produce a cell potential that is 1.10 volt for this particular type of setup. It means this setup will produce final voltage 1.10 volt, right? So because of the redox reactions, because of the chemical reactions, and the chemical reactions actually converted into electrical energy, it means it has a electric voltage. So such type of actually conversion is a spontaneous. So what you have studied in thermodynamics, that is any spontaneous reactions that cause the change of or conversion of chemical energy into electrical energy. So that is your measured by change in Gibbs free energy, right? So as you know that any particular spontaneous reaction, delta G is equal to minus negative, right? So if delta G is negative, it means this particular setup of electrochemical cell actually um, performs some work, and the work actually obtained in this setup will be because of the reduction of the Gibbs free energy change. So delta G is negative for spontaneous reactions. So if spontaneous reaction, so spontaneous reactions actually is due to because of delta G is negative. So overall, this electrochemical cell is due to the spontaneous reactions, and nothing but this is a electrochemical reactions, that is oxidation and reduction. So what happens since chemical energy is converted into electrical energy? So what happens here? That is actually this chemical energy is electrical energy is converted. It means there is we are getting some electricity from outside circuit, right? So this is your outer circuit. From the outer circuit, we are measuring electricity or potential of this particular setup. It means from the system to surroundings, right? So by the system, here work is due to the by the system, by the electrochemical cell on surroundings. So in the thermodynamics, you have studies about when the system works on surroundings, the work is negative, right? So here, and the maximum work depends on, that is directly proportional to n. What is n? Here n is the number of actually electrons transferred in this particular setup or electrochemical cell. So total number of electron, that is n, and this is the first factor. So the work actually will be done by this system is depends on the number of electron transferred from anode to cathode in a overall redox process, that is N. And another factor, maximum work, that is W max, is directly proportional to E0 cell. It means cell potential. It is the potential of the electrochemical cell. So at a standard state. So that is E0 cell. Now overall, if you combine these two factor, that is this, then W max will be actually NFE0 cell. Here we have actually broken the symbol, that is proportional constant, with F. So F, what is called actually Faraday constant. So this F is called Faraday constant. So W max is equal to NF E0 cell. And now this delta G is equal to W max, right? And since this W max is actually obtained by the system on surroundings, so delta G will be negative W max, right? So W max is nothing but NF E0 cell. So delta G is equal to minus NF E0 cell. Here delta G is negative, right? And N is the total number of electron transferred in this particular electrochemical reactions, and F is the Faraday constant, which is a constant have a value that is 96,500 coulomb per mole electrons. Now E0 cell actually that is calculated by E cathode minus E anode at a standard state. So if E0 cell, actually what happens, if E0 cell delta G minus NF E0 cell, if E0 cell is greater than 0, it means if electrochemical cell produce positive cell potentials at standard state, then delta G should be negative, right? It means electrochemical cell undergo spontaneous reactions and that converts chemical energy into electrical energy. And hence, if E cell is negative, E cell is less than 0, it means delta G is positive. Now, electrochemical cell does not work, but in this case, electrochemical cell work, right? So E cell must be positive for spontaneous reactions, right? Now what happens? And now E0 cell is actually E0 cathode minus E0 anode. Here these two values are standard reduction potential. These values, actually this is your, and these values, both values are standard reduction potential. So standard reduction potential of the cathode is higher because of the positive charge, and standard reduction potential of the anode is lower, and hence the potential difference is positive, right? Now in this particular zinc copper galvanic cell, actually the E0 cell is 1.10 volt, and you can see this is a positive quantity. So delta G will be negative. So such type of reactions actually thermodynamically favorable, and thermodynamically favorable means the electricity can be produced from this particular electrochemical reactions, right? Now, what happens in thermodynamics? We have studies delta G is equal to delta Z naught RT ln Q. So this is actually relation that has been obtained in thermodynamics. Delta G change in Gibbs free energy at any temperature is equal to change in Gibbs free energy at standard state plus R is the gas constant which have a value 8.314 joule per Kelvin per mole, and T is the temperature in Kelvin, and Q is called reaction quotient. Reaction quotient, and reaction quotient you have earlier seen that it is the ratio of the product, concentration of the product to concentration of the reactant. So now this reaction quotient can be converted into equilibrium constant. So K is called equilibrium constant. K is called equilibrium constant. It means if electrochemical cell is thermodynamically favorable, so it has a oxidation and reduction reaction simultaneously, but after passage of time, so there will be a equilibrium position, right? So it means in the previous reactions, you can say that if there is a two species A plus B, if it forms C plus D, so this is the symbol of the equilibrium. It means after passage of time, all the reactants is converted into this product C plus D, and but if all the C plus D further decompose to form such type of such a reactants, then the reaction is reversible. So redox reactions actually, if it is reversible, then the process actually involves equilibrium constant, and equilibrium constant is K is nothing but if concentration of C is multiplied by concentration of D and the ratio of A and ratio of B, right? So K, if K is very high, it means reaction is occurring in the forward directions, and if K is low, then reaction is occurring in these backward directions, right? So what is actually relations here? Delta Z naught is equal to minus RT ln K, right? And delta Z, as you know that it has minus NFE0 cell is equal to minus RT ln K. So this value minus minus actually cancel out. So E0 cell is equal to RT upon NF ln K. So this is the relation of electrochemical cell or EMF value of the cell, electromotive force or electrochemical potential of the cell is depends on the temperature. Here T is the temperature, and it also depends on the number of electron transferred in a particular electrochemical reactions, and R is the gas constant which is a constant, and F is also a constant, that is 96,500 coulomb per mole electron. Now ln K, so this is the equilibrium constant. Now this ln can be converted into log also. So E0 cell is equal to if this ln is converted into log, then we have to multiply 2.303 RT upon NF log of K, right? So if there is a standard state, right, it means T is stands for 298 Kelvin, R stands for 8.314 joule per Kelvin per mole, F 96,500 coulomb per mole electron, then E 0 cell 0.0591 upon N log K. Here this electrochemical potential of the cell depends on the number of electrons. If N is 1, then simply E0 cell is equal to 0.0591 log K, right? It means this electrochemical cell potential depends on the equilibrium constant, and it is directly proportional to the log of the equilibrium constant. It means greater the value of this log K, higher will be the electrochemical potential of electrochemical cell. So E0 cell is proportional to log K, right? And greater the value of K, greater will be electrochemical cell potential, right? Now, here we have shown actually a particular type of reactions in electrochemical cell, that is actually this is your first half cell and this is your second half cell reactions. So first half cell reactions occurs at anode, and at anode there is a oxidation, right? So oxidation, it means here lead is in oxidation state of 0, here this has +2 oxidation state. So this type of half cell reaction actually oxidation reactions, right? Now through the release of these two electrons, what is the E0 anode? That is 0.36 volt. And for another component here, that is lead dioxide, in presence of H2SO4, and that have actually aqueous solution of sulfate ion and hydrogen ion concentration, that will receive 2 electron, so that actually reduced. Here the oxidation number is +4, right? And here the oxidation number is +2. So here reduction takes place. So reduction takes place, it means the potential developed for this particular half cell reaction, that is E0 cathode, is 1.69, right? So both these values actually produce a overall reactions. So this overall reactions means lead in a solid state react with lead dioxide. These two components are in a solid state, and actually H2SO4 that have a aqueous ionic component. Then the product is lead sulfate and water, that is liquid. And the overall cell potential for such type of electrochemical setup is actually E0 cell means that is your E0 cathode, right, minus E0 anode, right? Here in both case this is standard reduction potential, but in another case you also E0 cell E0 read plus E0 ox. Standard reduction potential plus standard oxidation potential, if you add these two value, will produce electrochemical potential. So here that is 0.36, that is oxidation potential, 0.36 plus here 2.05, not 2.05, this is 1.69. So this is your actually 1.69. So both will add and that will be produce 2.05 volt. Here E0 cell for this particular setup is 2.05 volt. 2.05 volt. The value is comparatively high in case of zinc-copper electrochemical cell. In zinc-copper electrochemical cell, E0 cell actually was plus 1.10 volt. So this type of combination produce more powerful cell, right? And zinc-copper combination will produce less powerful cell. So the cell, the power of the cell, so that will depends on the nature of the nature of the materials or electrolyte and its reacting components and overall reactions. So here also two electrons are transferred in this particular reactions, and in case of zinc copper galvanic cell, two electrons also transferred. So the number of transferred electrons are same in both cases, but the overall cell potential is different. For this particular setups, the cell potential is very high, 2.05, and here in case of zinc copper galvanic cell, it is a 1.10 volt. So delta G will be more negative for such type of reactions. So the thermodynamically such type of reaction undergo rapidly, and in the previous case it will undergo slowly. But both type of reactions, they are actually thermodynamically favorable. So spontaneous reactions are important for the production of the electrical energy through the conversion of chemical reactions, right? So this is what actually happens in this particular setup. Now what happens? Delta G is equal to delta G plus RT ln K, right? If reaction quotient is converted into equilibrium constant, now this is NF E, that is NF E0, right, plus RT ln K. In case of, you know that zinc copper electrochemical cell actually K is concentration of Zn2 plus concentration of copper, and it is the ratio of actually copper 2 plus and concentration of zinc. Free metal has actually activity 1. So actually this stands for 1 and this also stands for 1 because of the activity of the free metals are actually 1. So 1 cancel. So actually K finally depends on the concentration of the Zn2 plus upon Cu2 plus, right? So what happens here from this particular setup? If U and F E is equal to minus, if we take it out, then what happens? F E minus RT ln K, right? So if it is F A, actually this is your not, in case of minus and F, so this minus minus actually cancel out. What happens naturally? N E is equal to, this is your NFE is equal to FE 0 minus RT upon ln K, right? So what happens? If you divide both side by NF, then E is equal to, and that is your, here this is your N, right? This is your the fundamentals equation. Actually, overall we can produce here E is equal to E naught minus RT ln K, right, upon NF. So this is the value of actually electrochemical cell potential E cell. That is the difference between the standard state electrochemical cell potential minus these factors. So it depends on the temperature and number of electrons and equilibrium constant, right? So for a particular type of equilibrium reactions, we have calculated so that will be actually for such type of particular reactions, actually what actually I have calculated. So ln K n E0 cell upon 0.0591 volt. So n is the 2, here 2 electrons, and E0 cell is the actually this value 2.05, and this is the constant 0.0591. So what happens? This is the your value. After calculation, we will get 2.3 into 10 to the power 69. So 10 to the power 69, it means the equilibrium constant is very, very high, right? So this actually delta G minus RT ln K. So if ln K is very high, then delta G will be naturally very high, right? So such type of actually setup, yeah, combination actually depends on the nature of the pair of the electrochemical setup. So this is your what? The relations as in the next page we have actually adopted. So this is the electrochemical cell. So electrochemical cell actually that is used to produce power or electricity, and this is basically based on the portable electronic device. Portable electronic device. So electrochemical cell is established in portable electronic device, and most important that is actually battery and fuel cells. So battery and fuel cell, so both are actually based on the electrochemical reactions, but in fuel cell there is one fuel and oxygen is required for the chemical reactions. So that actually both device will produce electricity, right? And most important thing is that this electrochemical cell setup has been used in electroplating. Electroplating. It means if you want to deposit a thin layer on a particular surface, then such type of electrochemical reactions will be implemented, right? And another one is corrosion production. Corrosion protection. Sometimes one material may undergo oxidation to form rust like iron. So if you want to prevent the corrosion from external atmosphere on the iron surface, then we have to set up a electrochemical cell, and that cell will actually protect the corrosion of iron metals. So because of the deposition of the another layer on its surface, right? So that is actually process of corrosion protections. Now another most important applications, reactivity. Reactivity. So reactivity of the metals in a particular electrochemical setup can be estimated through the knowledge of the electrochemical cell and cell potentials. And oxidizing, whether it is oxidizing or reducing, are redox natures. And redox natures, the most important application is redox nature, right? So redox behavior can be estimated through particular electrochemical cell reactions, right? So these are the actually applications which are based on the electrochemical cell and electrochemical reactions, and actually they involves electrochemistry. So this is the most important parameters and topics, so that will provide a insight into the deep understanding of electrochemical reactions, that is oxidation reactions and reduction reactions and cell potentials, and how electromotive force, that is EMF, is produced, and in what way they will be applicable for the industries or any other devices setup. So I think that is enough for understanding the electrochemical setup and electrochemistry. So thank you students for listening and watching this particular topics and its chemistry. So in the next video I will give you idea about what is actually another type of electrochemical cell, that is electrolytic cell. So what is electrolytic cell, that will be given to you in the next lecture. So thank you.